Hello everyone. Here in this video, we would like to solve a problem. The problem is like this. A part of the circuit is given to you as shown in the diagram here. This is the diagram that you can see. And you can notice there is a capacitor C here. This one. We want to know what is the energy stored in that 4 microfarad capacitor. Right. So, capacity is already given for you. C value is 4 microfarad. That is 4 into 10 power minus 6 farad. I know the capacity. I want the energy stored in a capacitor. We know the formula for the energy stored in a capacitor. We know the formula for the energy stored in a capacitor is half CV square. So I already know C. I need to know the V. So if V is known, I can simply solve this problem. So if you call this point as X, if you call this point as Y, you can say voltage across the capacitor is nothing but the voltage between points X and Y. In the other way, Vx minus Vy. So if I have to solve the problem, if I have to get the V of the capacitor, I have to calculate Vx minus Vy. If I know that, I can just substitute here in this and my problem is solved. So for that, we need to know how does the current is distributed in the between the points X and Y in the diagram, right? You can see here is a, see here is a 2 ampere current, 2 ampere reaching towards this junction. Here is a 1 ampere current reaching towards the junction. So sum of the currents reaching that junction is 1 plus 2, 3 amperes. As for the Kirchhoff's current law, currents leaving the junction is also going to be 3 amperes. So from this junction, current leaving is nothing but equal to 3 ampere. The 3 ampere will come up to here, right? So that 3 ampere after reaching this point, right, cannot travel this way because this is a kind of a open circuit. So that will try to travel this way. And look at this junction. 1 ampere is coming towards the junction, right? 2 amperes is going away from the junction. So thing that is missed in the problem is it is given in the problem. It is given, right? I am not taking it now. It is given in the problem, which is missed in the diagram. It is given in the problem that through this 4 ohms, a current of 2 ampere is leaving, right? This is given in the problem, which is missed initially. So I assume that this is the data given for you in the problem. So from here, 3 amperes is coming. After reaching this junction, 2 amperes will go this way. So remaining 1 ampere will come this way, right? Right. 1 ampere will come this way. And here you can see there is one more ampere. So this 1 ampere and 1 ampere will join at this junction. It becomes 2 ampere. And that 2 ampere will go this way as it is given in the problem. So the current flow is conserved at any of the junction. So what is missed in the problem is here a current of 2 amperes is leaving that junction that was missed in the beginning of the diagram. So we shall take that for granted. Now applying the Kirchhoff law at this junction. So I am applying only to this part, this closed loop, and let me apply the Kirchhoff law, right? So what I can say, starting from this point, Vx minus, I'm talking about this part now, Ohm's law, IR, right? So I is, as we have calculated, that is the value of the I is 1 plus 2, 3. So 3. And resistance is given to you in that problem as a, given that as a 5, right? So here it is given in the problem that the resistance is 5, therefore minus 3 into 5, because Why a minus? Because we have considered a direction. Let us consider a, say, clockwise direction like this. So potential drop current in this small element is in the direction the same as the direction that we have chosen, therefore potential drop across that is negative. So minus 3 into 5. Even here also the direction is like this, current is also going in the same way, so that is also minus IR, that is 3 into 1, right? Then let's come to this part of the problem, right? So I is, as we have calculated, out of that 3, 2 amperes has gone this way, so only the current coming here is 1 ampere, minus 1 into 2, okay, and this point minus Vy, that's the total potential difference. Of course, this all potential difference will be nothing but carry forwarded across the capacitor itself. So I can take this Vy on the other side and I can say Vx, that is potential here, that is potential here, and potential drop across this, and potential drop across this, and potential drop across this is the potential drop at this point Y itself. So if I simplify that further, Vx minus 15 minus 3 minus 2 equal to Vy. Get that Vy to this side. So Vx minus Vy is 15 and 3 is 18, 18 and 2 is 20. On the other side, that is going to be plus 20. So the potential difference across these 2 points is 20 volts. That means voltage across the capacitor is nothing but 20 volts. Once if I know the voltage across the capacitor, energy stored in a capacitor is further simple to solve. Half CV square. Value of the C is given to you, 4 into 10 power minus 6. Voltage square is 20 square, 20 and 20, right? So the value will be 20 and 20, 402, 800 into 10 power minus 6 joules, or 8 into 10 power minus 4 joules. This much of the energy is stored in the part of the circuit in the capacitor, right? That's how we have to solve the problem. Thank you for watching.